All right, let's do some really exciting physics with the law of conservation of momentum for multiple planes. Yes, we're going to do the hard stuff now. So here's a very typical two-dimensional conservation of momentum problem. Pretty much couldn't make it more typical than this. But anyways, we got two balls on a smooth table. Ball A is moving to the east towards ball B at 3 meters per second. Ball B is twice the mass of ball A and is initially at rest. After the collision, ball B moves off to the right at a right angle due south, while ball A moves off at an angle of 25 degrees north of east. Determine the velocities of balls A and B. So you got to solve for the velocities of each ball. Now, if all of that gobbledygook just made no sense to you because it was a lot of words, I hear pictures are worth 1,000 words. So there's my visual. Shouldn't have covered that up, but there's the before and after. So you got ball A right here, and it's moving across in a nice straight line at ball B. And if you ever played pool, it kind of nicks it. And so ball B basically goes straight down. Now, the odds of this happening are not too great. I'm sure it'll take a very subtle angle. But to make your physics much more straightforward conceptually, we have it going straight down. Also, to add the fun in, I hope you notice it says the fact that the balls are not equal sizes. All right, so ball B is twice the mass of ball A. So I made it visually bigger here. So ball B is twice the mass of ball A. So keep that in mind when you're doing your math. So again, your goal are to find the velocities of balls A and B. So on your mark, get set, science! I'll be back with the answer. There we go. There are your two answers. So if you do this correctly, the velocity of ball A is 3.31 meters per second, and the velocity of B is a negative 0.7 meters per second. So if you got it right, sweet. If not, let's walk through how we solve this. The first and foremost, most important thing that you can do is write out the law of conservation of momentum. Now, here's the kicker, though. You have to remember the law of conservation of momentum works in both planes. So we're going to write it twice. Once for the x plane, once for the y plane. So I always like to write it out. Okay, some people just want to jump straight into the equation they're creating, but I always like to write it out first so I can just remind myself how I'm doing. So again, we've got our two parts of the scenario. We've got the before. If I can write in a pen, we've got the before. All right, we've got the after. And then this right here, that's my collision. So the sum of momentums before the collision, that's these sums, equal the sum after the collision. And we're going to look at just the x-plane or just the y-plane. So we're going to isolate each plane independently. Yay, components. So I'm going to walk through the x-plane. As always, if you'd like to pause the video, try and work ahead, maybe realize the error of your ways, then feel free. But if not, I'm going to kind of plow forward here. So here's my here's my law of conservation of momentum equation in the x-plane. I always write out like this. Now, some people use some subscripts and all sorts of crazy stuff, but I like to reference my drawings. So I've got two objects beforehand, two objects before the collision. So they're each moving. Well, they're not moving, that's a lie, but I've got two objects, so I'm going to solve two momentums. So this guy right here is this guy's mass times his velocity, so m times 3, because I don't know the mass. This problem never gave it to me, which, by the way, should be a giant flag saying, I bet I don't need it. Like, you should always have that in the back of your mind. When they don't give you a mass, you probably don't need it. So don't freak out. Just leave it as a variable. So then this guy's momentum is 0 because he's not moving, so replace that with a 0. Afterwards, I again have two objects, so I'm going to solve for two momentums. Object A has its mass of m times its velocity, which, again, I don't know the velocity, but I can write it as a component. So if I look at this, it is moving in both with a y velocity and an x velocity. And I can just rewrite that in terms of their components. So Vx in this case is equal to V cosine of theta, because I was given the angle from the x-axis. And then Vy is equal to V sine of theta. So I can use that, and I can just put it in here. So that's what I did. So I've got VA cosine of 25, afterwards, the B1, object B, is not moving in the x-plane. It is moving, but it's only in the y-plane. So therefore, my velocity in the x-plane is 0. Okay, because we're just working the x-plane, so we only want the velocities in the x-plane. So then you can see that if I rearrange this, my mass becomes totally irrelevant, just like I had hypothesized. And then it's a matter of just doing your algebra, or your trig, I guess in this case, and you get 3.31 meters per second. So that's velocity A. Now once I have that, then I can look over in the y-plane. I can kind of use that to guide my understanding a bit. So now theoretically, maybe it was moving differently. You might have said, oh, I started with the x-plane and it was unsolvable. So for example, with this problem, if you would decide to look down the y-plane first, you would have quickly said, hey, by the time I get to here, I don't know velocity B and I don't know velocity A, so that's 2 unknowns, so that means it's unsolvable. So you could keep working as far as you can, but you will come to a point where you are stuck. So for example, this line here, when I subbed everything, I would have had 2 variables. Well, then just go look at the x's, see if they help you out. Okay, so you have 2 planes, so technically you have 2 equations. We could have a system of equations if I wanted to make this super tricky. And that's why I isolated it, so it wouldn't be super tricky. But I could have them both going off at angles, and you just have to have 2 equations, 2 unknowns, use some math tricks to solve it. So let's look at the y-plane. So again, I'm summing the momentum before the collision, setting that equal to the sum of the momentum after the collision. Before, again, I have 2 objects, I wrote mv plus mv. Afterwards, 2 objects, I wrote mv, mv. So it's a question of what are their velocities in each of these planes? Well, this guy has no velocity in the y-plane. This guy has no velocity in the y-plane either. So before, in the y-plane, we have a total momentum of 0. Afterwards, we have our Vy component here. So that's Va sine of 25 times the mass of the ball, plus the mass of the second ball, which is twice as big as the first. That's why I have 2m here, because this guy is twice as big. So if I wanted to call this m, I would say then this is a mass of 2m. All right. So then it's traveling at the velocity of b, and it's purely, like I said, it's going straight down due south. So I know it's all there. So then if I do some rearranging, do some algebra, I get to here. Again, mass all cancels out. Or I should say the constant of the variable of m cancels out. And then I end up with just one variable in terms of VA, and I have my VB. So I can take my VA from over here and I can put it right there, which then gives me my one variable, and I can then do my math and solve. And I find my velocity in the B plane to be, the velocity in the Y plane to be negative 0.7 meters per second. And if you look at it, it makes sense it's negative because it said it was going due south. Notice I didn't bring any negatives up into here. I just said, hey, it's a velocity. And I let the math tell me which way it's going. So it agrees with the math and the instructions. So it's all good. This would be the hardest type of problem we're going to give you at the honors level. So if you can solve this, you did great. Awesome. If you can't, you got to work on it. We will expect you to be able to do these though. So yeah, hopefully that was guidance. Hopefully it was help. Hopefully you did well. So I will catch you in class and see you next time.